So now we come to the third and last Fermion Monte Carlo talk by Professor Assaad. He's gonna go over the topics that you can see here, and immediately afterwards, he's gonna also give his second talk planned for today, which is on the models present already in ALF, and which constitutes the last ALF basics talk as well. So there are going to be two talks at once now by the same speaker. Thank you, Fakher. It's your turn. We can't hear you, Fakher.
So I was muted. Now I'm not unmuted. Can you hear me now?
Yes, it's fine.
Okay, so the last points are global updating schemes, stabilizations, and I will skip this point here because this has been done by Florian, and then I will talk about the supported codes in the ALF package. So why global updates? Well, we have single spin flip updates for the moment, sequential single spin flips, and there are many applications like electron phonon problems, etc., where we would need some better updating schemes. And so we have embarked on trying to include better they're not necessarily better, to be very honest, but to include different updating schemes in the ALF package. So this is a starting point. This is Langevin dynamic, it's called. And so the partition function is all again given by this is a generic form. And for this Langevin dynamics, we will assume that phi is a continuous field, right? It has to be, cannot be discrete. And what we will do for the Langevin dynamics is to throw in another time, right? So this is the imaginary time we already had. We'll put in a Langevin time, TL, so that these fields are dependent on a Langevin time. Now, once we have this Langevin time, we can define a stochastic differential equation for this field. So phi at Langevin time t plus delta t is equal to the field at the previous time. This is a force. This is the derivative of the action with respect to the field at time TL times delta t. And this is a stochastic variable, right? So this is white noise, which is sight, imaginary time, and Langevin time independent. And the expectation value at equal times, equal positions is equal to 1. So you should notice that in the discretization of this stochastic differential equation, delta t here comes linearly in delta t, but the noise comes as the square root of delta TL, which means that if delta t is small, then this term here will actually dominate, and it will be a rather noisy or sort of like a random motion on short times. So why is this okay? Well, you can sort of define a Fokker-Planck equation, and what you could do is you say, well, let's assume that I have at a given time, I'd like to define this is the probability distribution of having the field phi at a given time t plus delta t. Well, this is equal to essentially the integration of all the possible fields at a previous time. So this is p of phi prime of delta t. And then I have a delta function, so I will go on here, a delta function of basically phi minus, and I will open it up, and then here phi prime minus d of s over d of phi prime times delta t plus this white noise 2 delta t L. So we have delta TL here, and then eta of TL. So that's basically a white noise here like this. And I will have to average it like this. So what does this equation tells me? If I have, for example, the probability of the fields phi at Langevin time t, so this is not a delta t, this should be t here. T, if I have this, then I start with this field phi prime. I evolve it according to the Langevin equation, and that will be the field at the next time phi of tau of t plus delta t. And here I have to average over all the white noise. So you can if you this is the starting point to define what we call the Fokker-Planck equation. And if you just expand the delta function in this term here, or you expand actually this term here, then you will see that you'll get a differential equation for the probability distribution as a function of time. So this is the Fokker-Planck equation. And then you see that if I assume that I will come to a stationary probability distribution, which is time independent, then essentially this term here has to be equal to 0, which tells me that the equilibrium distribution is actually what I would like to sample. Okay, so this is on the paper, it works. Okay, so how do we implement this? Let's assume that this is our program for the long-range Coulomb repulsion. And what we would have to do is to calculate the action. So if I want to calculate the action here, I just have to put this in the exponent. So that's why I get a minus the log of the trace of this fermion propagator. If you take the derivative with respect to phi at a given position r and time tau prime, then you will get this term which comes from this part of the action, and then what you will obtain if you differentiate with respect to phi of I, then what you will bring down is basically the expectation value of C dagger of R, C of R at minus one, there's a factor 1/2 which comes in at tau prime, at time tau prime and R and equal positions. So this is so again, as in the single update scheme, the Green's function, the equal time Green's function, is the central quantity again to determine all the dynamics, the Langevin dynamics in this case. There's one thing which is rather fun here to see is that here you have an I. We showed that this was a sign-free problem, so the action is real. So you have an I. This means that essentially this quantity in the bracket has to be purely imaginary. And in fact, it is. If you look at this long-range Coulomb code at half-filling where you have no sign problem, because of I actually forget why, but because of particle hole symmetry, then the real part of the Green's function at the same position is exactly equal to 1/2. So this 1/2 will cancel the real part of the Green's function. You will always have something purely complex here, and that will be multiplied by I, and you get something which is real. So that's okay. So we can try this code, and it's actually extremely hard to make it work efficiently. And the reason is the following. So let me first give you an example and then discuss of why we are still working on this and where the problems are. So I'll take a step back. We have here chosen a very specific model. It's a 6-site one-dimensional Hubbard model at half-filling with open boundary conditions. And we took this problem because in this case, you can show that the action for a given field, right, is always strictly positive, right? Normally, an action, what you can show, even if you have no sign problem, what you can show is that action is always semi-positive definite, so it's bigger or equal to 0. And of course, you have no, I'm sorry, I'm looking at the determinant. What I want to show here is the determinant of M, the fermion determinant. Once you show the absence of sign problem, you show that the determinant here is like this. Okay, so what we have in our case is that the determinant is always bigger than 0. The action has the log here of the fermion determinant, so it never diverges. It's always something which is finite. So this is the case for the 6-site one-dimensional Hubbard model at half-filling, again with open boundary conditions. And you see that this code runs rather well. This is the Langevin result. Of course, since we have a stochastic differential equation and we have a discretization delta t, we put in a new error, that is then a discretization error. So we will have to extrapolate it in principle. And so this is the result as a function of different choices of delta TL, the Langevin time. And you see that it goes to the correct quantity. This would be this is a result we get with discrete Hubbard-Sutanovich transformation. So that seems good. The nice thing of the code is that it's a global update, right? You really at each time step here, at each time step, you change all the fields in the space-time lattice, so you could believe that you're doing better. The big problem of the method for the moment is that even if you have no sign problem, you have the determinant has zeros. If the determinant has zeros, the action has logarithmic divergences, then the force has also logarithmic divergences, and the code can go unstable, right? So this is one of the big issues, so for problems where zeros are present, this is a hard thing to control. So I won't take more time on this. Just tell you that we are still working on this. There's a branch where we have the Langevin code, which produced these results here. And so this is still work under progress. Our goal is Langevin to implement this, and so that people can test it. There may be some models where there are not too many zeros, so that if you are in this situation if you're in this situation, the Langevin dynamics works very well. If you don't have a too dense population of zeros, then that may be also okay. What we would also like to do is the hybrid Monte Carlo sampling. So this is an add-on to Langevin. It's a bit different, but rather similar. It has the big advantage of not introducing another systematic error because of the Langevin time, and it will not be unstable, but it can have problems with ergodicity. So this is still work in progress. Good. So I will continue and talk about stabilization. We've up till now we've assumed that all these codes are nice and numerically stable, and they are not. And the reason for this is the following: these matrices here, let's assume that I'm multiplying all these matrices B1 to B of phi of L. If you think of just the non-interacting case, this would be something like E just to minus. There's a total propagation of tau times the hopping matrix T. This hopping matrix has, if you take a square lattice, has a spectrum which goes from 4T, from minus 4T to plus 4T. That would be square lattice. That would be the spectrum of this, the eigenvalues of this matrix. And so you see that you have a huge scales, right? I mean, if I put this in the exponent, there are some scales which are going to grow as e to the tau times 4 times t, and then scales which are going to decrease to e to the minus 4 tau times t. So that's a huge span of scales. So if I start here and I take a 1, so the 1 here would be schematically saying I have a 1 matrix. The 1 matrix, and I can see that as a set of vectors which are orthogonal to each other. So if I take 2-dimensional, so these are my 1 vector and the other vector. And then when I propagate this 1 with all these b's, I will get this u, right? And essentially, all these vectors will collapse on the direction which has the biggest eigenvector, right? And the important information when I would like to invert a matrix is actually the difference between this vector and this vector, between these two vectors, and this will fall into noise, right? So if you propagate too much, this will fall into noise, and you will not be numerically able to distinguish if these two vectors are identical or not, right? So if these two vectors have a norm of 10 to the 20, 10 to the 20, and there's the difference is, in a certain sense, is only 1, then I will not pick up this one. So what do we have to do? We have to keep the scales separate, and the way to do it is to orthogonalize these vectors. So what I can do, I can say, okay, I start with this u, and I will do a Gram-Schmidt orthogonalization. So I take this vector as the reference, and I will then essentially take another vector here, which is orthogonal to that. When I do this, essentially what will happen is that my u of L is equal to a u1. So this is again an orthogonal matrix or unitary matrix in this case. D is a diagonal matrix which takes all the scales. So it has very big numbers and then very, very small numbers. It's just diagonal. And V1 is a unit triangular matrix. Okay, so this is how you would do it. So the point is that you will keep the scales separate. All the scales are here, and you will try never to mix scales up to the very last after the very last algebraic manipulation. So when I would like to build up those B matrices, so what I will do, I will propagate, for example, I would like to calculate U of 2L, then I will first go up to B of L, and then you do this UDV decomposition, then start with my U1 and propagate it again. And then these, out of these two things, I can do again a UDV decomposition and build up something systematically like this, right? And so that's a way of systematically separating the scales. And then, as I told you, you will have to be sure that the scales are always separate, and then you combine them only at the end. I don't want to say much more to this because um, I think it's a hard problem. Every time you have a new model, you have to be sure that it's numerically stable. So the code has in the info file, which is again very important, it has a variable called precision, green, mean, and max. So what this does is that we can update the Green's function, and we can calculate the Green's function from scratch. If everything is numerically stable, then the updated green function, the green function, equal time green function, which is calculated from scratch, should be the same thing. So we have a maximal difference for all the elements, that is this max, and a mean difference. So if you have something, if you look in the code, in the info file, if you have something like 10 to the minus 8 for the mean, and then 10 to the minus 10 for the 10 to the minus 10 for the, so 10 to the minus 8 for the max, and then 10 to the minus 10 for the mean, then you're doing very good, because the Green's function is normally something of the order of unity. So these are very good numbers. The present version of the ALF will stop. I don't know who implemented this, but I did not, but I know that it does now. It stops if the precision is bad. It will just stop right away and give you an error message. Okay, so just be careful about these two numbers, right? If you get weird results, go to the info file and try this out. We have different possibilities for there are different flags. Please look into the documentation that you can turn on or turn off for the way we do the stabilization. So you can play with this also if you have issues. I'd like to finish this point on one comment, which is the projective code, which has a remarkable feature. And this feature is that the Green's function for the projective code is independent on the scales. So if you remember, the Green's function for the projective code is given by this. So it's 1 minus this u bigger, u smaller, u bigger, and u smaller. The minus 1, and these u's bigger and smaller were defined like that by propagating the right trial wave function along the imaginary time and the left trial wave function backwards in imaginary time. So if I take this U, right, and I take this U as a set of vectors like this would be my matrix U, right? This would be the number of particles, and this will be the dimension here. Then I can do a Gram-Schmidt orthogonalization. This is U, a Gram-Schmidt orthogonalization of these vectors. So I will have new vectors, which are, these are all orthogonal to each other. And then what I need, so I need to do that, to have the identity, this D matrix and this V matrix. So we'll call this a small, this is n particle times n particle times n particle, and this is n particle, and this is n dim, right? The number of one particle states. Okay, so if you do this on like this for this side, and then this is essentially just the transpose, so you have a V smaller, D smaller, and U tilde smaller, then you can just put in this form. So this has all the scales, this has no scales, and the scales are here. You can just plug this into the definition of the Green's function, and you see that because of this -1 here, these D's, they just cancel out. The V's, they also cancel out. And what you obtain is something like that, right? So that's extremely interesting, because it tells you somehow that all the physics of the projector code is a sort of an orthogonal system, which always stays orthogonal, right? But sort of moves as a function of imaginary time, and that's the only information you really need. And so there have been many papers, I think by Alejandro Muhammad some time ago, trying to understand from a geometrical point of view, the physics of the projective Monte Carlo code. So that's a very interesting property. It's also very useful because in the projective code, we normally do not have any stabilization issues. Okay, good. Are there questions? The chat says no, so I will continue. Just interrupt. The ALF examples, this was done by Florian, so I will really skip that and then go to the second part of the talk. I'd like to be really on time today and talk about, so this is more supported codes in the ALF. So we have, there are some predefined codes, etc. So the codes we have are, there are 5 of them. We have Hubbard models, TV models, models with long-range density-density interactions, and Kondo lattice models. These all these codes, they come with an SUN version. Okay, and then we have another case of code. This is basically lattice gauge theories. That's where the Ising fields really come in. Lattice gauge theories coupled to fermion and Z2 matter. I'll explain this. All these SUN codes, right? They support all the lattices. So Florian told you about the lattices this morning. The lattices we have, they are the square lattice, the bilayer square lattice, the n-leg ladder lattice, the honeycomb, and the bilayer honeycomb lattice, and you can define other lattices if you wish. They support all the lattice. They come with symmetric Trotter decomposition, so that's built in, and they come with projective and finite temperature versions. Okay. The Z2 lattice gauge theory code is still work in progress. Lattice gauge theories are the lattice structure is really built into the definition of the lattice gauge theories, etc. So we have this only on the square lattice for the moment. It supports a projective and a finite temperature implementation, but there is no symmetric Trotter decomposition which is implemented yet. This is, it has to be done. So this is certainly under the rubric work in progress, still under construction. But we'll see if we do that or not. Good. So let me start with the SUN symmetric Hubbard model and tell you exactly where parameters are read and what we can do. So the lattice is defined in the var lattice part of the parameter. The model is also defined here. That's the Hubbard model. To define the hopping, right, on these models, we have these lists here. I'll make this bigger because I can't see it myself. And as Florian told you this morning, for the hopping, we have the possibility, these 4 entries. These are twisted boundary condition in the X direction, in the Y direction. You may know that twisted boundary conditions can be put in the bulk or through a gauge transformation just at the boundary. So maybe you would like to put them in the bulk. That's equivalent to the gauge transformation. So this is that's an option you have. And then what this gives you is a number of flux quantum which which traverse the lattice. So if you so what this means is that we have our lattice are embedded in a magnetic field. So if our lattices are in the XY direction, so my lattice is in the XY direction like this, XY direction, then I have a B field which is in the Z direction. And essentially the number of flux quantum, so B times the volume of the unit cell, so that would be the squared, times B times A squared divided by phi 0, that's equal to n phi. That's the number of flux quantum, this n phi which come into here. So this generates for all our lattices, this is for example for the square or for the honeycomb, this generates these beautiful Hofstadter butterflies, and you can do your calculations on these Hofstadter butterflies. So for example, this morning, we wanted to have a pi flux lattice. Well, for the pi flux lattice, what you could do is you take the square lattice and put in a pi flux per unit cell, per a pi flux per plaquette. That means exactly the number n phi divided by L squared is equal to 1/2. So this can be done. And then so these are general things, right? This is general. This is defined for all lattices. So that's why it's in this section of the code var lattice var model generic, right? And then you have something specific for all for different models. So for the Hubbard, we support bilayer lattices, and so what we have is essentially so this would be I mean, so I can get the lattice, that may be easier. The lattice, I think, is here. Sorry, the lattice is here. So for the bilayer Hubbard, what we have in this parameter file, we have predefined hopping. The T is like this. Then the hopping here, I'll put this bigger. The hopping here between the two is T perp. Then there is on the second layer a hopping T2. So I have T perp T and T2. There is in the predefined models, we always have a C4 symmetry. So we haven't broken the C4 symmetry. You can do that. And then you have a U and a U2, right? And then a chemical potential, which is there everywhere. So you find all these parameters which you have to specify. You find them in this specific list for the Hubbard model here. They are. And so ham T, ham chem, ham U, ham U2 for the second layer, the T perp between the two layers, and the U on the first layer. Okay. So that's what. So if you only take a square lattice, then of course the T2, U2, and the T perp, they will not be read. You can forget about that. Good. The model which is defined looks complicated. I mean, it's always hard to when you write in things generically, it becomes a bit complicated. We have two cases for the Hubbard model, this MZ equals true and MZ equals false. Let's start with the MZ equals false. So for example, if I put N SUN, so the N SUN, this parameter is read in the generic. N SUN equals 2, I have an SU2 model. And if you put MZ equals false, then the number of flavors will be automatically given by 1. So N flavors will be given by 1. So that will be the SU2 model. And so this is the hopping. As Florian told you this morning, this is the hopping, without gauge fields, right? So this is normally a real number. And then all the gauge fields are here in those parallel phase factors. And this is hopping site I, unit cell, site I, orbital delta, site J. So unit cell I, orbital delta, unit cell J, orbital delta prime. And the parallel phase factors need also the geometry. Our Hubbard interaction is given like this, as a perfect squared of the density fluctuations. So when you Hubbard-Tutanovich decompose this, you have a coupling to the density, and there is a chemical potential. Now, you can also use the case where MZ is equal to, so this one, MZ equals to true. And then when MZ equals to true, the logic is the following. Then the number of flavors is equal to 2, because I will couple the Hubbard-Tutanovich to the magnetization. So I have a spin up sector and a spin down sector. And the NSUN will be divided by 2. So NSUN will be divided by 2, and that will be equal to 1, right? So that if you put NSUN here 2, and you put MZ equals 1 here, then the code will automatically put NSUN will divide it by 2 and put the number of flavors equals 2. Okay, so this is discussions within our team of if we can do this better. Some people think we can do this better, etc. So that's what will happen. And this is for if you put MZ. So I'll repeat myself. If you put MZ equals true and N SUN equals 2 in this parameter, then the code will divide NSUN by 2 and do this and use these parameters. So in this case, you will again have the same Hubbard model, right? This is just the interaction is now coupling to MZ, and you have, of course, the chemical potential and the hopping. Just note this NSUN equals 2. Okay, so again, this is chosen such that, if you take MZ or not MZ, you get the same answers. Then you can, if you want, you can generate models with NFL equals 2, number of flavors equals 2, and then SUN bigger than 2 could be 4, etc. And you will go to saddle points to antiferromagnetic saddle points, for example. Good. So let me give you an example of this. Is there a question?
I have a
yeah.
I have a question. So I mean, can I do the for example SU3?
Yes, you can put 3. You can put 3, but you'll get a dreadful sign problem.
Okay.
So
it mainly works for even numbers of n.
Yeah, it only works for even number of n's. SU3, try it, you will get a sign problem.
Okay.
Right. So that's at least for these repulsive interactions, you get a sign problem. For the TV model, I'll come back to it afterwards. You can do SU3. An example is can we do something?
Fakher?
Yes.
Can I ask another question?
Yes.
So when you choose the MC decoupling, does the NSUN variable in the parameter file have to be even because you divide by 2?
It has to be yeah. So
yeah.
it's checked in the code, and if it's not even, then you have a stop. You have an error message.
Okay.
Right. It's divided by 2, and so you can put in that's it. So each decomposition, Hubbard-Satonovich decomposition, corresponds to a saddle point, right? And so this decomposition here corresponds to a magnetic saddle point. This decomposition here corresponds to a paramagnetic saddle point. If you take this code here and you put n going to very big, or you put n equals 4, then you will break the SU2. You will break essentially the symmetry of the problem will be SU n divided by 2 times SUN divided by 2. That's the symmetry of the problem. So that would be the spin up sector, the spin down sector, which you can generalize to higher orders, and you will essentially be able to stabilize stripe phases, etc. I won't go into details here, but that's possible to do. Now, an example to show you that what you could do. Let's assume that we want to simulate a heavy fermions, a periodic Anderson model. Maybe some of you know what it is. It's essentially a model where you have spins, which are here. There's no hopping between the spins. There's a hybridization V, and there's a term T here, right? That would be the periodic Anderson model. And this is one of the classics, right? Many body classics. So you put ham T equals 1, ham T2 is 0. Ham T perp would be the hybridization. Ham U is equal to 0 because you just have conduction electrons with no interactions here. Ham U2 would be the UF. So that would be the F electron here. And then let's forget about all these possibilities of putting in magnetic fluxes. Let's take an NSU2 equals 2 and the number of flavors equals 1. And then you can reproduce I'm sorry, this comes from this paper. This is a paper from the 90s, 95s of Doug Scalapino, Richard Scalater, and Vecchi. I don't actually never met him. And then this is basically as a function of V over T, you have one phase which is magnetically ordered. That's where the RKKY interaction dominates. And you have in here another phase where you have a Kondo insulator. This is a Kondo insulator. And so you have, you can see these are the spin-spin correlations at pi. Here you see that they grow here. They grow as a function of system size. So this is a symmetry broken phase. And here they certainly are intensive. They don't grow anymore as a function of system size. So you can, these are just results which you can produce with this Python script, but it takes a bit of time because we go up to 10 by 10 and the results are not so bad. And so you can reproduce this plot with this Python script, Hubbard, PAM, pi. Okay, so it works, and the VC is more or less the same as you get in this paper. This is an old paper, so they weren't not even as precise as this. Okay, so let me go on. We have SUN TV models. Same thing, you can do, this works for all the lattices. We need, again, so a TV model is a model where you have nearest neighbor interactions. So these are this V2, that's nearest neighbor interactions in the second plane. V perp, these are nearest neighbor interactions between the two planes. And these are TV, these are these are nearest neighbor interactions in the first plane, hopping between the planes, and there's a chemical potential. The form of this lattice, the form here is this way. So you define a hopping, right? With all the phase factors, etc. And out of this hopping between adjacent sites, you can define your, I mean, this is bond hopping. You can define the full hopping here. And the interaction is nothing but the hopping, right, to the squared, right? And you really have to take the same hopping here and here. Otherwise, you have problems with gauge gauge invariance, right? If you put an A here, you have to put the same A here. Otherwise, your thing doesn't become gauge invariance. And we did the mistake, and you get crazy results. So be careful. This has this is something squared. This is summed over all the ends. So to get a balance between this term and this term, that not to get one term completely dominating, you have to divide your V by N. The same thing was also done for the Hubbard model. And here's again the chemical potential. The sign structure here is a bit tricky. Because when we specify a T, we mean actually minus T in front of the hopping. So here, if I specify in the model ham V is equal to V and ham T equals to T, then the model which will be simulated is a minus T and a minus V, right? So you will not get a sign problem here if V, which you specify here, is bigger than 0. Now, this is a case where you can use, I think I talked about this Majorana idea of how to get rid of the sign problem by using Majorana fermions. So this is a very nice case where you can do it. If n is odd, so 3, that was a question before, you will have no sign problem in the absence of a magnetic field at half filling, that means mu equals 0, and for any v bigger than 0. If you take n even, you will have no sign problem for v bigger than 0 and mu equals 0. That means I did not specify the magnetic field, so I can put in a magnetic field here. And if you dope it, right, you will have no sign problem for v bigger than 0, no magnetic field, and as a function of doping, so mu is not equal to 0. So you can do quite a lot. I mean, what will happen here is essentially you will generate a superconducting. I guess you will generate superconducting. As an example of this model, this is an exercise. The TV model for 1D, so you have programmed this in principle, or you will program this in the exercise, and you can check it. We're using this code. This is just spinless fermions on the one-dimensional lattice. If you have spinless fermions, this V term, these are just 2 lines of calculations, actually goes into a density-density interaction. This only works for spinless fermions, of course. So the minus V here goes to a plus V, and then you can, from here, you can use Jordan-Wigner transformation to show that this TV model in this formulation is identical to a spin to an XXZ model, where JXX is equal to 2T and JZZ is equal to V. So you can simulate actually the one-dimensional Heisenberg model. If you take JZZ is equal to JXX, you can, this is a very well-studied model, and these are beautiful papers of Peschel, which tell you exactly what the critical exponent should be. There is the SU2 symmetric point where you have 1 over R decay of the spin-spin correlations or the density-density correlations. If you go to the Ising phase where this is bigger, then it becomes long-range ordered. It's an Ising long-range order, and if you take this smaller than this, then you have a Luttinger liquid phase. And if you take this, -2 of this, then you have phase separation. So this is a very well-known model, which you can benchmark your ALF with this as much as you want. Questions? Good. So let me go on. Long-range Coulomb interactions. We use this code to do all our work on graphene with long range, where you would need a long-range Coulomb interaction. So I simplified the notation here now. I is basically a unit cell and an orbital. This is implemented like this generically, again, for an SUN problem. What is in the code for the moment is a matrix V of ij, which is given by U. So U would be the on-site part of the long-range Coulomb, or so the Hubbard U. and then I have a tail 1, and then I have an alpha. I have to specify this alpha. D is the minimal distance between two orbitals, which I can calculate from my lattice and or my unit cell information. And this is a distance, so we have to be a distance between 2 points. So this is I plus delta I minus J plus delta J, right? Or minus delta J here. And I, because I would like to define this on a torus, is the way, I mean, there are different ways of doing this. The easiest way was for me to do is to just take the minimum over this quantity. So if you have any 2 points on the torus, you know, these 2 points could be, you could take this distance or the other one, which would be, you go over the edge. I will take the middle, the smallest one, okay? There are other ways of putting in long-range Coulomb on periodic lattices, so you can do that. For the moment, this is what is done in the code. It's very modular, so it's extremely easy to change the code so as to read in this full matrix. We could do this in an hour or not, or less, even less. If you don't specify, you could have somehow a file on your starting directory. The code could inquire if this matrix, if this file is present, and just read the V of ij's from there, and you could run. The only thing you have to do is to be sure is that V has to be positive definite, otherwise you cannot do the Hubbard-Stotanovich. These are the parameters. So everything is pretty clear. There is the U, the alpha, which determines the tail, the magnitude of the tail of the Coulomb repulsion. The only thing, we know this percent change, this is a bit special for this code. What we do for this code is that we go into a basis where S0, if you remember, for this code, the S0 was given by something like a field phi of I, V minus 1 ij, and then phi of j with a minus like this, and there was a 2, right? That was my S0. And so we go into a basis where this V is diagonal, and in this basis where V is diagonal, we do a simple sampling with respect to this probability distribution S0 of here 10% of the fields. If we do this for all the fields, then the acceptance rates goes crashing down. So we do it only for, let's say, 10% of the fields, or you can, then it turns out to work okay, right? So you can read this in the documentation. This is very well described in documentation. You can test this code. So this is a nice little test between, you know, if I put alpha equals 0 in this code, right? If I put alpha equals 0 in this code, then I should get the Hubbard model, right? Alpha is equal to 0, there's no long range. So you can run the code. The Hubbard Hamiltonian for alpha equals 0, the MZ equals true. You for these parameters, you get this energy scale with very good energy, with very good error bar. If you use more or less the same time, then you will get this with this long range Coulomb. If you take alpha equals 0, and you see, you get the same result. I mean, 1.8, 1.9, my error is on here. So I'm doing very good. So these are equal, right, within the error bars. You see that the error bar is much bigger here. There are two possibilities. One is that this is something which couples to the density, right? You couple here to the density when you do the Hubbard-Stotanovich. Generically, when you couple to the density, then the fluctuations of the double occupancy are much bigger than if you couple to the Z component of the magnetization. So that's one thing. And also this code is a bit slower because the updating is a bit more involved, right? So you lose something with this long range code. Questions?
Yeah. Have you experimented with, for example, a Rydberg interaction or a van der Waals interaction?
No, try it. Is the V positive definite? Maybe not.
I'm not sure. I have to think about it.
But you see, that's a nice thing of this code is that to answer this question, you can do it right away. Just we can modify the code within, as I said, an hour to be able to read this as an input, right?
Mm-hmm.
And then you can try your stuff, right? Try different interactions. This has to be positive definite. If it's you know, otherwise you will the code will stop. Also, it tests if it's positive definite, analyze it. If it's not positive definite, it just stops. I think I can check.
Okay.
Good.
I'll have to think about it. But
Think about
it's
it.
good
and
to
then do that. Yeah.
Thank-
Other questions? Good. Condo. So this is the first. So this is a heavy slide. I'm very sorry, but this is the first case where the model you write is not the model you put into the computer. You have to be able to rewrite the model to be able to put it in a form where you can do efficient computations. Huh? So that's let us go through this. So these Kondo Hamiltonians, they are only defined, of course, on bilayer system because I need an F and then conduction electrons. So I need magnetic impurities and that. They're defined like this. Okay, so this is even to, so they define like this. I have again my hopping here with all the magnetic fields, etc. A chemical potential. Now the chemical potential is only on the conduction electrons, and you'll see why afterwards. Then you can put in a Hubbard interaction on the conduction orbitals. These are these points here. There is no hopping on the F, so I call these, the two are the F orbitals, so that's here, F and C. Okay, so this F and C. And then there is a Heisenberg type interaction, a Heisenberg interaction between the conduction electrons and the F electrons on a given site. So there's a Heisenberg interaction here between those two sites. So I call it with J. Okay. Now, of course, we want to put in the SUN version. Why not? Let's make our life complicated. So we would like to put the SUN version of this model. So T of A are essentially the generators. So you have n squared minus 1 generators of SUN, and we choose this normalization, right? So that the trace of TATB is equal to 1/2 delta AB. That's the same normalization you would have for the Pauli spin matrices divided by 1/2. They satisfy exactly this this behavior, right? So that's the same normalization. Then my T of A hat is just like, you know, how you define a spin operator, and this is also the spin operator, but for the Fs. So we fermionize the F spin, and there is a constraint. So NC is the number of electrons on the C's, and there is a constraint that I have exactly. So I write that this operator is equal to a number n divided by 2, meaning that there are no fluctuations which are allowed. So at every time, every moment in imaginary time and in space, I have exactly this number of electrons on the F thing. So if you take n equals 2, that would be means here I would have 1, and that would be something really like a spin. If you have a spin degree of freedom, you have no charge fluctuations. You have exactly, if you fermionize a spin degree of freedom, you have just 1 electron per site. Okay, so this is what we would like to put in on the code, and so you have to manipulate everything a bit. The first thing is to use identities of SUN generators to show that this object here can be written as like this. This is a D. This is a hopping between C dagger and F. So basically what this does is an exchange. I go from C, I exchange an electron with one color from C to F, and I'll take another color from F to C, right? So that's an exchange. And there's another piece here, which is essentially equal to the density. Now, if you are in the physical Hilbert space where this is equal to exactly n/2, so I can replace this by exactly n divided by 2, right? And so this cancels with this, right? So this gives you nothing. And this again is n/2, n divided by 2. So this is just a constant. Okay? So I can forget about this term in the physical Hilbert space. Okay, so now what do? We know how to write this, but what we don't know how to do is to constrain everything to the physical Hilbert space. Because when I put things in the ALF, I will also have charge fluctuations on the F electrons. What we can do is then to relax the constraint and impose a Hubbard term on the F sites. Okay, so we'll do that. And actually then what goes into the ALF, this is the Hamiltonian we actually solve. We have our hopping, we have our chemical potential just on the C's. We have now this is the same one as this one here, but we add here UF on the F sites. And this is essentially this term, right? But which I wrote in a perfect square. So if you take the trouble to do that, I mean, you will get this term here. The cross terms come in twice, so I have to divided by 2. So I have a 4 instead of a 2 here. And the cross terms, this term d squared will go away with this one because of the I. Okay. So you can use one field for this, and you can use one field for this perfect squared. And at this point, I think you should see that it's possible to put it in the ALF. The real question here is, how good are we at imposing the constraint, right? We would like to impose the constraint of we really want to have this. This has to be the case. The key point is that this, you can go through all the equation, you will see that this local constraint, right, commutes with this HQMC, right? So if you impose the constraint on one time slice, it will be satisfied all over the imaginary time propagation. That means that you can really, before running the code, you can show that NF of I minus N divided by 2, this is a local problem, right? You can solve that and see how quickly this goes to 0 if I just calculate it for here. And that will go to E minus beta UF divided by N. So you will exponentially, project onto the correct Hilbert space. And you know exactly this factor. So before you start the code, you know exactly what you have to, for a given UF and beta, for a given beta, and N, what type of UF you have to choose so as to project onto the correct Hilbert space. Is that okay? So here's the example. Here's an example, SU2, right? And what we're calculating is to check. So beta is constant, 4 is constant, the JK is constant, and I'm going to vary UF and calculate this quantity, which is essentially the fluctuations of particle number on the F site. And this line is exactly what you would theoretically expect. In this case, it's essentially E of minus beta UF divided by 2. So this works like a charm. And you see, what you also see is the spin-spin correlations at pi for the F electrons. And you see that, so this has to saturate to the physical, this is the physical value, right? Because that's where you get into the correct Hilbert space, and you see that it converges more or less, depending on how precise you want to be, but it converges more or less here. It's more or less like converged. Okay, so if I take this UF 1.5, then I'm good enough for any practical purposes. Okay, so that's how we implement the Kondo lattice, and it works beautifully well. We can do a lot of work with that. The variables for this class are rather simple. We have hopping, chemical potential, UC, UF, and the Kondo coupling. Okay, and you can do SUN, and these plots here are generated by this Kondo pi script, which you can, if you follow this link, you will find it in our ALF directory or in the pi ALF. Questions to that? Okay. Now let me come to the most complicated model I've ever done. Well, maybe some people have done more complicated like Johannes, but this one is tricky. And this is a lattice gauge theory of so these are fermions. So let me tell you what corresponds to, and then I'll show you a simple example which is pretty cute, which was done in collaboration with Martin Hohenadler. And so what do I have here? I have the variables. These sigmas are Pauli spin matrices on a link, right? A link is site between I and J. And so there will be, this is a fermion, right? So the fermion hopping, if you want, will be dependent on the sign plus or minus of this dynamical variable. This is a dynamical variable because here this variable beats, on each link I have a minus G sigma X. That means that this sigma Z can go up and down as a function of imaginary time. So these are my fermions, right? These are my variables on the gauge fields, they're called. There will be gauge fields. There is a plaquette term, right? For those people who are very well versed into this. And I can put in a Hubbard U term here. Now, on top of this, to make our life more complicated, but the physics much more interesting, we have Pauli matrices on sites. These are called matter fields, tau Z of I. And these tau Z of I, they can couple like this to the gauge field. So you should see that the gauge field at the two extremities, I and J, carries what we call the jargon is a Z2 charge. And this has also a Z2 charge. This has a Z2 charge. So this is Z2 neutral. So I can put in a term like that. This, the matter field, they also beat with a frequency sort of like h. And there is this object here. This object here can be identified to a fermion, right? And because this is what people call an orthogonal fermion, you couple it to Z2 matter, it becomes a fermion. At least the quantum numbers are the fermions. I'll come to this later. And so so this fermion can hop from site I to J. Okay. So let me tell you that one of the, when you talk about lattice gate theories, you have to think about constraints. And the point is here is that there is one local conservation law, which is the fermion parity, right? The fermion parity, this star operator, and this tau x for the matter fields. If you start in a given sector of this, you will always stay in this sector. And it's actually pretty easy to see, is that let me work in a basis where the sigmas are in the x direction. Every time I hop an electron from I to J, I have to flip this bond field, right? Because, I mean, the sigma z will flip the sigma x. So that means that this will change sign, but this will also change sign. Okay, so this, when this changes signs, this changes sign. The same thing happens here for the fermion hopping. As soon as I take away an electron, right, from site I have to also automatically apply a tau z. So if I'm a tau x basis, this tau z will flip the tau x from x to minus x. And so this will flip sign and this will change sign also. So again, you can go through all the possible processes and you will see that this Q of I, if you start the code in one system, in one sublattice, then so for one constraint, then it will always stay there. So we've done a lot of work with these things, and and we're having a lot of fun, etc. But it's uploaded in the code. So let me give you. I have 3 more minutes, Jefferson. So let me give you an example, which is rather cute, and which is again an example which allows us to test things, right? To test things between different codes. Let's assume I would like to generate. I would like to simulate the Hubbard model, but I'd like to simulate the Hubbard model, so we can do this. We know how to do this, but I would like to do this now in a very complicated way by fractionalizing the electron into 2 quantities. What we will do is so this is called a Z2 Slate spin formulation that was introduced by Manfred Siegrist. And so this type of fractionalization. And so what we write the electron. I will split it into a spin, an Ising spin, and a fermion, right? And when I do this, of course, there is a gauge redundancy, which I have to take into account, the Z2 gauge redundancy, which I take into account. Now, let's look at the states. These are my fermionic states, right? So these are if I take one site, I have the possibility of having up, down, right? A 0 and an up, down, a doubly occupied site. So we'll identify this this is the tau x, right? Tau x value, so that's minus, plus. So if this is, the fermion parity is here equal to -1, so I would like here to have a minus. The fermion parity here is equal to 1, so I'd have to have a 1 here. The fermion parity here is equal to 1, so I would like to have a 1 here. Now I can do, so of course, these are the 4 physical states. Well, I claim that these are the physical states, but I have another 4 states here, which would have Q equals -1. So what is Q? I was too quick. Q is the position, the value of tau x, so I'm in a basis where tau x is diagonal, times, this is what I call the fermion parity, right? -1 times the number of fermions there are on the site. So I'll repeat this. The fermion parity here is -1. This is then -1, so it gives me 1. This is, the fermion parity is 1 times 1, that's 1. Fermion parity here is 1 times 1 is 1. So this is the Q equals 1 sector, right? Now I have another sector, which is the Q equals -1 sector. The fermion 1 parity is minus, but I take a plus, that's -1. This is 0, this is 1 times -1 is 1. This is then 1 times -1, this is then -1, right? So this is the Q equals -1 sector. So of course, if I look at this, I have these 4 states. If I look at this, I have these 8 states. So I have to get rid of something. And what I have to do is to put in a constraint. So I'll put in the constraint and say, I would like to work in a Hilbert space where Q equals 1. So Q equals 1, it'll be enforced all the time. And so I have a dictionary between this state, and that's a 1-to-1 mapping. If I can formulate everything in this notation, then I would be able to simulate the Hubbard model. Okay, so how do I go on? Well, I can say that I can use -1 to the side. This is an identity is equal to 4 times n of I minus 1/2. You see that? So this fermion parity is nothing but 4 times the Hubbard interaction. Right? If I take U equals 1, it's 4 times the Hubbard interaction. Now, because I have imposed, I will say that Q is equal to 1, then I can multiply this Q, I can multiply here both sides. Let me do this slowly. I can multiply both sides by tau x here and tau x on both sides. Tau x goes away here, and I say that tau x is equal actually then to the Hubbard interaction divided by 4. So now I have this Z2 model, right? And in the sector Q equals 1, if I use the constraint, right, which I have, then this model here should give me exactly the same results as the Hubbard model, right? So if I can simulate this with this constraint set to 1, then I'm simulating the Hubbard model. Okay, so let's try. We can do that because this is just a subclass. You know, this model here is just a subclass of this, right? If I take this, right, then I kick off everything sort of like, I mean, so I kick out this, 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 I keep this, I keep this, I kick out this. So this is exactly the model I have here, right? So I can simulate this with the Z2 matter code. There's one thing which is still important. Give me one more minute, Jefferson, is how should I impose the constraint in the ALF, right? And actually you don't have to do it because you can show that this HZ2 commutes with this constraint Q of I, that's equal to 0. Since Q of I is an Ising variable, it's plus or minus 1, then at 0 temperature, it will order. And I know that it orders, because I can measure it, it orders ferromagnetically. So if you go to 0 temperature, this Q of I will be automatically 1 everywhere or minus 1 everywhere. Now, if it's 1, then I've chosen this representation. If it's minus 1, I've chosen this representation. But I could have kicked out any one of the two and I would get the same thing. So let's try it. You know, let's try and see if this works. And so you can simulate this with the Z2 matter. This is on an 8x8 lattice, U over T equals 4. And you have to go to rather low temperature because the constraint will be imposed only at 0 temperature. And you see that this is N of K. This is what you get from running the Hubbard code. So this is the Hubbard code. And this is what you get from running the Z2 code, Z2 matter code. And it's remarkable to see that, you know, let's say pi has 0.0665, 0.666, but the error is here. So that's 1, 2, 3, 1, 1, 2, 3, 1. So that's okay. There we go, right? You can go to the other things also, and they're really. So this is a cross check. It's actually not so easy to program this. You can go into the documentation to see how it works. I think that there is still a lot of beautiful physics to do with this Z2 matter. I think this is just starting. The code has issues in a long autocorrelation time, so this is still an issue. Some parameter range are extremely slow. Imposing the constraint dynamically is very hard. So this is, you know, this is a research code, but it's at least it fits into the ALF. So that's maybe the most complicated code we have to deliver with the ALF. Okay. So with this, I'll conclude all the things. So, you know, I think the conclusions are a bit trivial. I mean, if you're here, you maybe agree with this. What are the challenges? Of course, the sign problem remains a challenge, maybe we won't solve the sign problem so easily for generic models, but at least we can try to see if we can be intelligent enough to enhance the class of models which are sign-free and thereby learn more on interactions in fermionic systems. I think that one of the things which one should be able to progress. I'm not saying that we have been able to so well, but I think it seems to be possible to try to get better updating schemes so as to cure critical slowing down near critical points, and for cases of models like electron phonons, for example, that's a classical model. And then there's another question, is that all our Hamiltonians or all our methods are slow, right? I mean, n to the cubed times beta, okay, supercomputers are getting bigger and bigger, you get more and more cores, but n to the cubed is still very slow. And the question is it possible in some way to generate methods which are efficient and which scales better? I think there's the hybrid Monte Carlo, which we talked about briefly, but it doesn't work all the time compared to the BSS. So this is still, I think, a bottleneck. So these are I think this is maybe too hard. I mean, solving the sign problem, I think, is too hard, but maybe enhancing the number of models is possible. This is hard, but possible, and this is very hard, but maybe possible. Okay, so thank you very much, and I'll take some questions now.
Okay, thank you very much, Fakher. I think that's a very clear exposition of the models that I have in ALF right now. Do you have any questions?
I do have a comment regarding this global update. It only has the Langevin method you were discussing today, right? The Langevin dynamics.
Yeah.
I know that for some of the, like, for example, for the SU2 Howard model, what you can do is flip like one spin in all the imaginary times.
Yeah.
Yeah.
So there is a global updating right here, right? I mean, so there is a routine in the ALF code which allows you to define arbitrarily global updates. Okay.
Okay.
So you can look at the documentation, and I forget the name of the routine, but you can say, okay, I do a couple of sweeps, right? And then I do a couple of global updates, and you have to specify the global update. Basically, the code asks you, here is the in the Hamiltonian module, there's a routine, and here is the present configuration. Propose another configuration, right? And I'll try my luck with this other configuration. So that's what you have to specify. And there, of course, it could say, well, I think Richard Scalator was doing this. It's just to take a line in imaginary time and to flip all the line, correct? That's what you had in mind.
Yes.
Right?
Yes, exactly.
So this is something which is implemented. It just takes a minute or two to implement, and you can try your luck with this. So yes, the answer is yes. This type of global updates is present. It's very easy. So you maybe know that some people have been using machine learning to propose global moves, right? So this, I think, was this Xiang Meng, and they were calling this self-learning algorithm. I don't know if you're aware of this, but this is proposing global moves on an optimized model such that the acceptance is not too bad, right? So this is something you can implement very quickly in the ALF because you have this routine where you can really specify global updates.
Okay.
The trick with global updates is that you have to be clever, right? I mean, you have to be clever because if you change too many spins at once, then the acceptance rates goes down, right?
Yes.
So you have to be clever what to update. You have to understand. You have to first understand the physics and then impose a global update. And understanding the physics on the basis of Hubbard-Ratanovich fields, which are maybe not directly related to a physical variable, I think is sometimes a bit challenging. I mean, that's my opinion. Maybe some people have different opinions, but that's my opinion.
Can I add a comment to this?
Of course, I will show you. Yeah, yes.
So I was working and trying to use those global updates, both that I stay on a fixed imaginary time slice and then update many fields on many sites on the same time slice. But I was also trying to study and learn the physics hidden in the auxiliary fields and then propose global updates for many time slices. And I thought that I had a good understanding of the physics hidden in these auxiliary fields. The problem was that the initial moves that I proposed had an acceptance probability of, I don't recall the numbers exactly, but let's just say 10 to the minus 13. So essentially, they never got accepted. And then with the physics input that I at least claim to have figured out, I could improve this core acceptance ratio from 10 to the minus 13 to 10 to the minus 8. So yes, it was quite a bit better, but 10 to the minus 8 is still way too small to effectively be accepted. So I think the problem is that you have to understand the physics kind of exponentially well, because the acceptance rate goes down exponentially if you increase the cluster size. And that's quite tough in general.
Yeah, no, I totally agree. Thank you.
And also later on, when I will give an overview, I probably will walk through all the functions that can be called or should be called from the main file, and I will show at least the signatures of those two functions where you can define those global updates.
But maybe here we have to cut short the questions session because we are already 10 minutes over time.
Okay.
Because let's first thank again Fakher. Thank you very much. So I'm gonna stop this recording and start again in preparation for the next talk.